Dear students, welcome back to the logic simulation chapter. Today we are going to introduce the second logic simulation technique, event-driven simulation, which was invented in 1965. We will introduce one-pass algorithm followed by a two-pass algorithm. In the last video, we talked about compiled code simulation. It has two problems. First, the gate delay model was not considered in the compiled code simulation technique. The second one is that compiled code simulation is oblivious, which means that it forgets the old results. It has to rerun all the code every time we start a new cycle. For example, in this circuit, suppose that the first input vector is 0, 0, 0, and then in the second cycle, we apply a slightly changed vector 1, 0, 0. For compiled code simulation, it runs the first cycle and then it forgets all the results in the first cycle. It has to rerun all the code for the second cycle. From this figure, we can see that actually only a small part of this circuit changed. But for compiled code simulation, we need to rerun the whole circuit. This is a waste of time. So, the idea of event-driven simulation is very simple. We evaluate a gate only if there is an event at its gate input, where an event means a signal value change. A gate with input event is activated, so we only evaluate the activated gate. This can save a lot of runtime if there are a few events. For the same example, in this circuit, A is rising from 0 to 1. This is called an event. And gate G2 is activated. In the event-driven simulation, we only evaluate gate G2 instead of all the 4 gates. So event-driven simulation can potentially be faster when there are a few events in the circuit, which is oftentimes the case. Now we present the one-pass algorithm with zero delay. First, we read in the initial condition of the circuit and we fetch a new input vector. We put active primary inputs fan-out gate to a queue, which is a first in, first out queue. And then every time we evaluate a gate from the queue, if there is no output change, we simply ignore this event. If there is an output change, we would put G's fan-out gate to the queue. This process is repeated until there is no more gate in the queue. So let's see this circuit. For example, we have A rising to 1 event and the B rising to 1 event. In this figure, we will use this notation. Parenthesis G VG plus means that gate G is changing to VG plus. At the beginning, we have 2 events, B1, A1. When we execute this event, the fan-out gates of these 2 events are G2 and G1 respectively. So we put them in the queue. Then we take out the first event from the queue, which is G1. Because there is no signal change at output of G1, it was initially 1, so we don't have any new events generated. And then we take out the second gate from the queue, which is G2. Output is rising to 1. We execute this event and put the fan-out gate G4 in the queue. And eventually, we would evaluate gate G4 to be 0 at the output. Since there is no more gate in the queue, we are done. This is a very simple one-pass event-driven algorithm. Now it's time for you to do an exercise. Given the same circuit, suppose that A is 1, C is 1, and the B has a rising transition. Now please finish the simulation using the one-pass event-driven algorithm. Please pause the video. Now, are you finished? So let's see the result. First, the fan-out of input B is G1. So we put G1 in the queue and we execute this event. So the output of G1 has a rising transition, which has two fan-out gates, G3 and G2. So G3 is then evaluated to 0. And then we put the fan-out G4 into the queue. And then we evaluate gate G2, which has a rising transition. Remember, we also put the fan-out G4 into the queue. And then we evaluate G4 to be 0. And please don't forget there is one more G4 in the queue. After that, we are done. So is your answer correct? The one-pass algorithm seems to be very simple. However, when we consider the gate delay, things can be very complicated. Now let's consider all the gate has 1 nanosecond delay. And we slightly modify our one-pass algorithm in this way. Every time we get a new event, which is G, VG plus at timestamp T from the queue. In this algorithm, we use this notation G, VG plus at T to indicate an event. That means the output of gate G is changed to VG plus at timestamp T. If the output does not change, then we ignore this event. If the output does change, we execute this event and we schedule a new event. So this looks like a very good modification of our one-pass algorithm. Now let's try this algorithm on our exercise, where B has a rising transition at time 0 nanosecond. From now on, we would ignore this nanosecond for simplicity. We just simply write it as B, 1 at 0. So now, when we evaluate gate G1, the output of G1 will rise to 1 at time 1 nanosecond. So we push this event into the queue. And then at time 1 nanosecond, we pop out this from the queue. Since we have a signal change, we will need to evaluate G3 and G2. So the output of G3 will fall to 0 at time 2. Also, the output of G2 would rise to 1 at time 2. And now we have 2 events in the queue. Suppose we pop out the G3 event first. So we evaluate G4, which has a rising transition at time 3. This is because at this time H is equal to 0 and J is now equal to 0. So the output of the NOR gate will be evaluated to 1 at time 3. Now let's execute the next event, which is G2 change to 1 at time 2. So we will schedule a next event. At this time, H is now 1 and J is 0. So we will evaluate the output of G4 to be 0 at time 3. And then we pop out the last event, which is G4 becomes 0 at time 3. Please note that at time 3, we have signal K rising and then falling at the same time. This simultaneous toggle of signal K is a little bit strange. Does it cause any problem? In the previous slide, although we obtained the correct answer at the end, this may not be true all the time. Consider this case. Suppose that the order of 2 events are swapped. Then we would execute G4 equal to 0 first, and then we execute G4 equal to 1 later. So eventually, we will get a wrong output. This is a very bad algorithm because the correctness of the output depends on the event order. So one pass algorithm can generate a wrong output due to the simultaneous signal toggle. This is a very bad thing because we don't know the implementation of this queue. So we cannot guarantee the correct order of these 2 simultaneous signal toggle. So next, we will introduce the 2-pass algorithm, which avoid the simultaneous signal toggle problem. This slide shows the 2-pass algorithm. The rectangle in the middle represents the first pass. The gray rectangle on the right represents the second pass. In the first pass, we execute events where LE is an event list. The event list is a priority queue of events sorted by time t. In the second pass, we evaluate gates. We have an activity list LA, which is a simple list of gates. Every time we advance a new timestamp t, we retrieve a current event from the event list LE. From here, we enter the first pass. We get an event from the event list G, VG plus. If VG plus and the VG are the same, that means the new value and the old value are the same. Then we simply ignore this event. If new value and old value are different, then we update the signal value, then we append G fanout gate to the activity list LA. This is for the second pass. We continue this loop in the first pass until we finish all the events in LE for a given timestamp T. And then we move on to the second pass. Every time we get a new gate from the activity list LA, we evaluate gate G and schedule a new event G, VG plus at time T plus the gate delay of gate G. We keep in this loop of second pass until we finish all the gates in the activity list. Because all the input events to a gate are evaluated together, so we can avoid the simultaneous signal toggle problem of a one-pass algorithm. Now let's try this new two-pass algorithm on the same example where B has a rising transition. At time 0, we execute this event. The fanout gate G1 is put in the activity list. In the second pass, we schedule the event G1 output rising to 1 at time 1. Now we move on to time 1. We execute this event and the two fanout gates G2 and the G3 are put in the activity list. And then in the second pass, we schedule two events. G3 is falling to 0 at time 2 and the G2 output is rising to 1 at time 2. And then we move on to time 2, where we have two events going on. They put the fanout gate G4 in the activity list. In the second pass, we evaluate G4. So G4 output is supposed to be 0 at time 3. And then we execute this event and finish the simulation. Please note that we only have one event scheduled for G4, so there is no simultaneous signal toggle problem. So the two-pass algorithm correctly solved the problem. Now let's see a more complicated example. We use the same circuit, but this time the gate delay of G1 and the G2 are 8 nanoseconds. G3 is 4 nanoseconds and the G4 is 6 nanoseconds. For the input side, we have A rising to 1 at 0 nanosecond, and then it falls to 0 again at 8 nanosecond. So we have a pulse like this. And the input C is falling to 0 at 2 nanosecond, and input B is falling to 0 at 4 nanosecond. So now let's try this two-pass algorithm. At time 0, G2 is activated, so we schedule an event H rising to 1 at 8 nanosecond. At time 2, G1 is activated, so we schedule an event which is E rising to 1 at 10 nanosecond. And so on, we schedule an event E falling to 0 at 12 nanosecond. At time 8, we have input A falling to 0, and we also have a scheduled event H rising to 1. So we have two gates in the activity list, G2 and G4, and we schedule two events where H is falling to 0 at 16 nanoseconds and K is falling to 0 at 14 nanoseconds. At time 10, we execute a scheduled event where E becomes 1. Because E is already 1, so we don't need to do anything. So there is no more activity going on after E1. At time 12, we execute a scheduled event where E is falling to 0. So now we have a real event, and the G2 and G3 are put in the activity list, and we schedule two more events in the event list. At time 14, K becomes 0 because there is no more fan out, so there is nothing in the activity list, and so on. We execute all the events. At time 22, we finish all the simulation. After event-driven simulation, we can now plot out a timing diagram to show the signal waveform. Input A is having a 0 to 1 and a 1 to 0 transition. B has a falling transition and C has a falling transition. Signal E has a falling transition at time 12, and the waveform of H is like this, waveform of J is like this. Finally, the output falls to 0 at time 14. Event-driven simulation can provide us many detailed information. These waveforms are pretty important for high-speed circuit and also for delay fault testing. We will look into more details in the delay testing lecture. In this plot, we also observe that there are some green arrows which are false events. That means the signal actually does not change. For example, at time 10, E is rising to 1, but actually E is already 1, so we don't need to do anything. This is a false event. Similarly, at time 20, we have a false event here. At time 22, we have another false event. False events are actually useless. Can we remove them? This is a good question. We will discuss it in FFT later. Now it's time for you to work on this quiz. Suppose that we have one input rising at time 0. Please fill in this table using the two-pass algorithm. Please pause the video and work on this quiz. Now, are you finished yet? Let's see our answer. G1 is in the activity list, so we scheduled an event at time 8. At time 8, we execute the event and put G2, G3 in the activity list. Also, we have scheduled two events. H is rising to 1 at time 16 and J is falling to 0 at time 12. and we execute this event, which produce a k rising at time 18, and we have this event which produce k falling at time 22. So this is our answer. Have you got it correctly? Now we have shown you the algorithm to run event-driven simulation. So how about the data structure to implement the event list LE? There are two types of implementation. The first type is a simple linked list data structure. As we can see from the figure, we have a linked list of the timestamps from T0 to T1 to Ti. They are sorted by the timestamp. Under each timestamp, we have a linked list of events. The advantage of this data structure is that the timestamp is pretty flexible. You can insert, for example, an arbitrary delay between T0 and the T1. However, the problem is that it's slow to search. Suppose I want to search for Ti. We need to go through T0, T1, and finally we can reach Ti. So this may not be a good idea when the list is pretty long. The second implementation is using a cyclic array data structure. This is also known as a timing wheel, proposed by Ulrich in 1969. The array is arranged in a cyclic fashion. Suppose that each slot represents a timestamp. Under each timestamp, we have a linked list of events. Suppose the current time is now n delta t. The next timestamp will be n plus 1 delta t. The third timestamp is n plus 2 delta t, and so on. The maximum time slots available is n plus l delta t. The advantage of this data structure is that it's easy and fast to search. Suppose I want n plus 3 delta t, I can directly access this time slot. But the problem is that the time slot is fixed. So we cannot have something like 0.5 delta t. This is not allowed. And there are only L slots available in a cycle. You cannot insert an arbitrary slot between two existing slots. This is not allowed. So in summary, in this video, we have introduced the concept of events, which means signal value change at timestamp t. The event-driven simulation only evaluates gates with event at the gate input, so this can save the CPU time if the number of events is very small. And we also consider the gate delay, so we can draw the waveform after event-driven simulation. We introduced two algorithms. The one-pass algorithm is simple, it consumes less memory. However, simultaneous signal toggle problem can generate wrong output. So we move on to the two-pass algorithm. It avoids the simultaneous signal toggle problem, but it consumes more memory for event list and activity list. Finally, the data structure of event list can be linked list or cyclic array. Linked list is slow but flexible. Cyclic array is fast but the number of time slots is fixed. So now we have already know compile code and event-driven simulation. Let's compare these two simulations. The advantage of compile code is that it's pretty straightforward. The implementation can be easier. However, there is no gate delay, and the compile code simulation is oblivious. That means we need to rerun the code for each cycle. This is suitable for circuits with high activity. The event-driven simulation considers the gate delay. We only simulate events in the circuit, so this is suitable for circuits with low activity. In most of the case, event-driven is a good idea, but the algorithm of event-driven simulation is more complicated. Finally, we have some FFT for you to think about. In our lecture, we mentioned that false events are actually useless. Can we remove this false event? Can we modify the two-pass algorithm so that we can save some CPU time? Is that possible? Second question. One-pass algorithm is good, but it cannot handle the simultaneous signal toggle. Can we propose a modification to the one-pass algorithm so that we can handle this simultaneous signal toggle problem? The third question is about cyclic array. We mentioned that there are a limited number of L slots in a cycle. So what if we have a remote event? That means the event is outside of n plus L delta t. What can we do? Thank you for watching.